Now let's apply constraint optimization in the production side, specifically in the cost minimization. Our intention here is to minimize the cost of production as a function of the labor and capital that the production uses, subject to a production function which is the goal, for example, of the day. For this case, we have a target which is already the quantity. And what we want is to try to minimize the cost. So the direction of improvement is towards the origin. W here is the wage and R is the rental rate of the capital. For example, the rental rate of machinery. As in the previous cases, the Lagrange function is simply the cost function, which is the function that we want to optimize, minus the lambda times Q, because it's a number, this is a constant, which is the target of production, minus the production function itself. From the first order conditions, with respect to labor, capital, and lambda, we will obtain a very important property, which is that the marginal product of labor divided by the marginal product of capital is equal to the ratio of the wage divided by the rental rate. This is known as marginal rate of technical substitution. Let's apply that concept in the next example. Here we have that Carlo works as a manager at the Cloud 99 store. He has two inputs, labor, which is used for maintenance and cashiers, and capital, which is used for installation, machinery, and cash. The quantity of total product sold in million items per year is given by this production function, in which L is labor and K is capital. The wage paid to the labor is $35,000 per year per worker, and the rental rate is $15,000. The question here is, what is the optimal allocation for labor and capital when the quantity sold is 48 million items, and what is the optimal cost? This is our standard cost minimization problem, in which we need to minimize the cost of producing using labor and capital subject to a production function, which was given in the problem. In addition, we have the wage, the rental rate, and the quantity. So let's replace all of those values before we proceed. So the wage is 35,000 times L plus the rental rate is 15,000 times K, subject to Q, which is 48 equals 8L to the 0.7, K to the 0.3. Now remember that in order to use the restriction, which in this case is the production function, we need to leave one of the sides equals to 0. For convenience, let's subtract both sides by 8L to the 0.7, K to the 0.3. So both sides we will subtract the entire function. In that sense, here on the left side, we will have 48 minus 8L to the 0.7, K to the 0.3. And on the right hand side, this minus this will be equals to 0. And remember, we always need to have it in that way because our restriction, when we write it in the Lagrange function, has to be equal to 0. So again, our first step is to set up the Lagrange function, which is equals to the objective function minus lambda times the restriction. And remember, the restriction always has to be equals to 0. So let's replace that. In this case, the Lagrange function is a function of L, K, which is labor in capital, and lambda. This is equals to the objective function, which is 35,000 times labor plus 15,000 times capital minus lambda times the restriction, 48 minus 8L to the 0.7, K to the 0.3. And remember, all this part is equals to 48, so 48 minus 48 is equals to 0. So in other words, the only thing that we are doing to the objective function is subtracting a 0 value. The second step is to use the first order conditions. We take the Lagrange with respect to labor. Here we have that is 35,000. Then the derivative of this term with respect to L is simply 0. Minus lambda times the derivative of 48 with respect to L is 0. But now we have to be very careful here. Here the constant part is minus 8k to the 0.3. The variable part is L to the 0.7. And the derivative of L to the 0.7 with respect to L is 0.7 L, and then 0.7 minus 1 is minus 0.3. And then we set all of this equals to 0. Then let's continue with the Lagrange with respect to capital. So the first term, the derivative is equals to 0 because it does not contain k. For the second term, the derivative is 15,000 minus lambda times, again, the derivative of 48 with respect to k is 0. Here the constant part in this case is going to be minus 8L to the 0.7 times the derivative of the variable part, which is k to the 0.3. The derivative of that is 0.3 times k to the minus 0.7, because 0.3 minus 1 is minus 0.7. And we set that equals to 0. And finally, we have the Lagrange with respect to lambda. That is, the derivative of these two with respect to lambda is 0. So the derivative of lambda with respect to lambda is 1 times all the function that is being multiplied by the lambda. So this is 48 minus 8 L to the 0.7, K to the 0.3. And this we set equals to 0. So let's move all of these three equations to the next page. So let's simplify a little bit. The partial Lagrange with respect to labor was 35,000. Now minus times minus is plus. 8 times 0.7 is 5.6 lambda, K to the 0.3, L to negative 0.3, and this is equal to 0. The Lagrange with respect to K is 15,000. Minus times minus is positive, and then 8 times 0.3 is 2.4 times lambda times K to the minus 0.7 times L to the 0.7, and this is equal to 0. And finally, for the case of the Lagrange, we can multiply everything by minus 1, and as you can see here, we can obtain 48 minus 8 times L to the 0.7, K to the 0.3, and this is equal to 0. So here we have three equations. And the procedure itself is the same as in the case of the utility optimization. Let's move these two terms to the right-hand side. So this is going to be 35,000 equals to minus 5.6 lambda K to the 0.3 L to the minus 0.3. And here we have 15,000 equals to the minus 2.4 lambda K to the minus 0.7 L to the 0.7. And as before, we will divide them. Now from here, notice the following. Lambda and lambda disappears. And then let's multiply both sides by 2.4. And let's divide both sides by 5.6. This means that this and this cancels out, and this cancels out. Also the negatives cancel out. Then we can also cancel 3 zeros here. So far, the only part that we have remaining from here is 2.4 times 35 divided by 5.6 times 15 equals 2. Now notice, from the case of K is to the 0.3, and in the denominator, we were subtracting 0.7. If we move it to the numerator, we will change the sign. The same happens for L. We move the 0.7, which was positive, to the numerator, changing the sign. Now, there is something very interesting about this operation itself. 2.4 times 35 divided by 5.6 times 15, if you do it in your calculator, that gives you equals to 1. On the other hand, K is elevated to 0.3 plus 0.7 is 1, and L is to the minus 1. In other words, here we have 1 is equals to K over L. In other words, K and L are the same in this optimization. And then, as in the case of the utility function that we solved before, we will replace this relationship that we obtained from the first two equations into the third one. So let's replace in the third equation. So before we replace it, let's just move all this to the right hand side. So this was 8L to the 0.7, K to the 0.3. And this was the original restriction. And now K and L are the same. So instead of K, let's write L to the 0.3. This is 48 equals 8 times L. 0.7 and times L to the 0.3 is L to the 1. Let's divide everything by 8. This means that the optimal value for L is equals to 6. And because L is equals to K, K is also equals to 6. So this is our optimal combination of inputs. And then the final step is to calculate the optimal cost. And remember, the cost function was 35,000 times L plus 15,000 times K. So let's replace L equals 6 and K equals 6. So this is 35,000 times 6 plus 15,000 times 6. And this is equals to 300,000. So this will be our optimal cost.